Okay, so some of you might be wondering why Schrödinger's equation has the particular form it does. So why does energy play such an important role in the evolution of the quantum system? Okay, so this video is sort of a brief video to address this concern. It's mostly to point you in some direction if you are interested in pursuing this any further. Okay, so just to recall, the Hamiltonian of the system is the energy observable. Its eigenstates are the states of definite energy, etc. And Schrödinger's equation says that the evolution of the system is intimately tied to the Hamiltonian. Right? It's a differential equation which says that which governs the evolution of the system, and it intimately ties the change in the state to the action of the Hamiltonian on the state. So where does all this come from? So it turns out that the answer lies in this beautiful connection between symmetry and conserved quantities in quantum mechanics. And this goes back to work by Emmy Noether, who is regarded as the greatest female mathematician in history, the greatest woman in mathematics in all of history. Okay, so let's see how we can derive the form of Schrödinger's equation. So the first thing we observe is that from the axiom of unitary evolution, we can derive with a little bit of work that the time evolution operator must look like e to the minus I m t for some Hermitian operator m. Okay, so for some Hermitian m. Okay, so let's take this for granted. So now what we are really trying to understand is why is m equal to the Hamiltonian? Okay, and we don't want to prove that m must be equal to the Hamiltonian. We want to sort of argue that it must, right? So we'll provide a justification which is going to be actually quite compelling. Okay, so what this relies on is a theorem which says that if A is any observable corresponding to some physical quantity, so if A measures some physical quantity that's conserved, meaning, for example, A corresponds to momentum or angular momentum or energy, it's some quantity that's conserved over time, then A must commute with M. Meaning that A times M equal to M times A. Right? Now, I hope you realize that matrix multiplication in general doesn't commute. So for example, if we look at our operators X, the bit flip operator, and Z, the phase flip operator, right? Then what's X times Z? Well, so it's 0, 1, 1, 0 times 1 minus 1, 0, 0, which is what? You get 0 here, minus 1, 1, 0. And what's Z times X? It's 1 minus 1, 0, 0 times 0, 1, 1, 0, which is what? 0, 1, minus 1, 0. Right? These are not equal. So in general, if you're given two general operators, they will not commute. But if A corresponds to any conserved quantity, then it must commute with the time of this Hermitian operator M, which occurs in this unitary evolution. Now, let's see, why does this follow? So let's sketch out a proof. So let's let psi be the state of the system at some time, and let psi prime be equal to u psi be the state which is e to the minus I m t, psi be the state after an infinitesimal interval of time t. So now what does it mean to say that A is a conserved quantity? A is conserved quantity means that if you look at the expected value of A under psi, so psi A psi, this must equal to psi prime A psi prime. Okay, but what's psi prime A psi prime? Well, psi prime is u psi, so it's u psi and then a u dagger psi. Okay, but this equation holds for all psi. Since this holds for all psi, this implies that in fact A must equal to u dagger A u, right? And so u dagger A u is of course just e to the I m t a e to the minus I m t, which if you expand out with a Taylor expansion, this is to a first order equal to 1 plus IMT times A times 1 minus IMT. Remembering that t is very small, so higher order terms don't really matter here. And this further is about A plus IT times MA minus AM. And so since A is equal to this, it tells us that this must equal to 0. Right here I'm ignoring the order t squared term which comes from this product here, because t is tending to 0. And so now if this is 0, then that tells us that MA equal to AM, which is really what's saying that A must commute with M. Okay, so what have we learned so far? What we've learned is that first what we said is that just from the fact that we have unitary evolution, it follows with a little bit of work which we won't go into, that U must be of the form e to the minus IMT, where M is Hermitian. And the second thing we know is that if A is conserved, then A must commute with M. Okay. So now there are various quantities that might be conserved. There are things like momentum or angular momentum, but one can argue that these are accidental conserved quantities. These are conservation relations which may or may not hold. So for example, conservation of momentum, well, it may or may not, momentum may or may not be conserved depending upon, for example, if you have a change in potential energy, then momentum is not conserved. Okay, energy is always conserved. Right? Remember, we are working non-relativistically, so energy is always conserved. Okay, so there must be some intrinsic reason. So what we're saying is that there must be some intrinsic reason why M and H commute. And what we are going to reason is that, in fact, the most natural intrinsic reason why H and M commute is that M is some multiple of H, right? So H equal to, say, right? This is what we are really claiming, that there's some constant which turns out to be H bar, such that our energy operator, the Hamiltonian H, is H bar times M, where M is the operator which describes the evolution of the system, and that's what we're claiming. Okay, so maybe let me actually go through it quickly. You can read about it in the notes if you're interested, but let's just go over it. So the rough form of reasoning is that, well, in order for M and H to commute intrinsically, well, the one way we can imagine it is if H is actually some function of M, some polynomial in M in general. And then the next thing to show is that, in fact, there are other physical considerations. So this is, this was to make sure that H and M actually commute. But the next thing to show is that, in fact, there are physical considerations which imply that if H is some function of M, this function must necessarily be linear. Okay, and that has to do with saying, well, suppose that our system consists of two disjoint pieces, 1 and 2. So this has an associated Hermitian operator M1. This has an associated Hermitian operator M2. This has a Hamiltonian H1. This has a Hamiltonian H2. Well, then the energy of the composite system, if our system consists of these two disjoint pieces, the energy is clearly H1 plus H2. But on the other hand, the operator associated with this, the Hermitian operator, must also be M1 plus M2. And so H must be equal to F of M1 plus M2. But we are claiming H, but on the other hand, H1 is F of M1, H2 is F of M2, and so F of M1 plus M2 equal to F of M1 plus F of M2. And so that tells us that F must be a linear function. Okay, this is maybe too much for most of you, but I just added it in for those of you who are interested. It's certainly not in any way required for anything that follows. Okay.